Okay, now, this week, we're going to talk about a very interesting phenomenon, which is that there are hierarchies to what we mean by contextuality, levels that we will consider one stronger than the other. I think that this week we will be able to talk about strong contextuality, which will frame our discussion of this hierarchy. Let's see, I don't know if we will get through the whole thing today. So we have hierarchy of contextual. And so the idea is that there is going to be a notion of probabilistic contextuality, which is weaker than possibilistic, which is weaker itself than strong contextuality. So there's three sort of paradigmatic examples here. There's the Bell model, which gives you the probabilistic. This is what violates CHSH. There's the Hardy model, which gives you an example of possibilistic. And then there's GHZ and or the PR box, which gives an example of strong contextuality. Interestingly, we will start off with this and also this, and time permitting, we will talk about the possibilistic version in this lecture, if not in the next one. And this whole, interestingly enough, this whole discussion of a hierarchy or strengths of contextuality comes from a sort of seemingly unrelated question, which is which events, I'll put this in quotes because I haven't specified what I mean by an event, which events are possible in a measurement And so to give away a little bit of the punchline at this level, I'm going to specify something like an empirical event, those events that are possible given a particular sort of empirical setup, and more like global events. And then the distinction or the way that these things overlap is going to say a lot about this hierarchy to some extent. So I just want to recall some of the stuff that we talked about recently, which is that we have something that we were calling a measurement scenario. Where X is a set of measurements O is a set of outcomes. We have that there's a set of contexts. So this thing is equal to a set over C, which are subsets of our measurements, such that the union of C equals X. That is, I'm going to have a set of these things are going to be called contexts. And these are exactly going to correspond in quantum theory to jointly the measurable observables. And what I mean by this is just that when we sort of take the union or collect all of the possible contexts together, At least every measurement is in one context. So given a context, there are certain outcomes that we can observe. These are the sort of outcomes of our joint measurement. So for C and C, the possible outcomes are given by O of C is all maps S from C to O. So that is, a context could be Alice measures X, Bob measures Y, and S is all possible joint outcomes for this measurement setup. So maybe Alice gets outcome R and Bob gets outcome S out of 0 and 1. So this is all possible tuples 0, 0, 0, 1, 1, 0, 1, 1. The empirical probabilities these are going to be precisely labeled by P of C, which is, and S, this is greater than or equal to 0 for every joint outcome in C. So I have all those tuples. So one thing is that these are non-negative. The other is that the sum for S in C, P of S equals 1, so that this is a probability distribution. So we have in particular that an empirical model is a collection. P is equal to PC. And we'll give an example. And these collection of C's, PC's have to be compatible. That is, P of C restricted to C intersection C prime. And I'll give a little example of this, but this is just a new notation for the non-signaling conditions. Equals P of C prime restricted to C intersection C prime. And this must hold for all possible C, C prime, and C. Oops, a little excited. So let's give an example of this. Say that we have X is equal to, and this is maybe not such an interesting scenario, but I have X, Y, Z, or just labeling my measurements. These could be in quantum mechanics, labeling just some observables. I say that my outcome set is basically arbitrary. I have D outcomes. And then I say that my set of contexts are like this. X, Y in one of them, and Y, Z in the other. And I'll just call these C, C prime. Just to give you guys an example of what the non-signaling conditions look like, I have a non-signaling or compatible distribution if for C, I have something like the probability of, what is this S? These S's are precisely the ones that take me to a particular value. X goes to T. I'll just write it in this notation. This is some value 1 to D, and Y goes to U. And P of C prime of S prime, say, is P of C, and Y goes to, I'll just write it as U prime, and Z goes to V prime. Now, what is the non-signaling condition going to give me? It's precisely telling me that what is the intersection between C and C prime? C intersection C prime is precisely the set Y. And so what I'm going to want is that the sum over the X outcome for this one is going to be equal to the marginal over Y. The sum over the Z outcome is going to give me also the marginal over Y, and so these should agree. But the idea is that the sum over T of P of C of T comma U equals the sum over V of P of C prime of U comma T, or V rather, and that this should equal P of C intersection C prime of U. So this is just very similar to the non-signaling equations. We just call these, this is a different sort of a notation, but it's just saying that when I have these sets on their overlap, the marginals should agree. Now, let P be an empirical model for the measurement scenario then I want to define the support of a distribution. So we are going to say that the support of a probability distribution is going to be given by all of the events or outcomes on that context such that PC of S strictly greater than 0. So we would say that these are the events that are possible empirically. So let's maybe give a little example. So, a very simple example. We take x equal to xy. This is all the measurements that we have access to, and just we take our outcomes to be 0, 1, and we just have a single context x, y. Maybe just, and this is C. So what are the, and say that we have a probability distribution. We have P of C, and the possible events are you assign 0 to x, 0 to y, 0 to x, 1 to y, 1 to x, 0 to y, and 1 to both of them, and say that this is 1/2, 0, 1/4, 1/4. So in this case, the support of PC is precisely equal to the tuples 0, 0, because the probability is strictly greater than 0, 0, 1, 1, 0, sorry, not 0, 1, 1, 0, 1, 1. So we would say that these events are possible, whereas this event here is impossible. Okay, so we are going to sort of elaborate on this notion with something that we'll call a global support. So what is the idea of a global support? We are going to think of having an empirical model, so a set of empirical probabilities PC, and we are going to look for the global outcome assignments, so the non-contextual value assignments, such that whenever you look at each context, the corresponding outcome for that context relating to that global support will also be positive. So it'll help to just write down the definition, and then we're going to look at a bunch of examples to hopefully drive the point home. So consider a global outcome assignment that I will call G of OX. So how can I think of this G? This G is going to be, if I have a set X of, say, however many, so this is a capital X, a set X of measurements, a global outcome assignment is going to be giving a value G of Y for all Y in capital X. So maybe in something like, if you had recalled that in the CHSH scenario, a global outcome assignment would be something like assigning a value, say 0 for when Alice does her first measurement, 1, say when Alice does her second measurement, 0 for when Bob does his first measurement, 1 for when Bob does his second measurement. So we can just think of this as a string of outcomes, one for each measurement in our set. And we have the following question. So given an empirical model P, is G, the global outcome assignment, consistent with P? I'll put consistent in quotes because now we'll sort of define what we mean by this. Let's consider x1, x2, x3 as our measurements in this example. We take O equals to 0, 1, and we have a set of contexts equal to Cij, where Cij is equal to xi, xj. Now, suppose we are given an empirical model, which is like this. P is equal to, and so what do we need? We have the context 1, 2, 0, 0, 1, 1, 0, 1, 1. Each context has 2 measurements in it. So when we look at the outcomes, we're assigning 0 and 1 to each of these. So we have the context 1, 2, 2, 3, 1, 3, and the probabilities are 1/2, 0, 0, 1/2, 1/2, 0, 0, 1/2, 1/2, 0, 0, 1/2. Unassigned piece of homework. Check that this is no signaling. I will do the first one for you. We have to marginalize to the first measurement. Here, that means summing over the second. So if I just look at the 0 outcome on measurement 1, I sum these two together and I get 1/2. To get the marginal for the measurement 1 in a different context, I would sum these two and I get 1/2 again. So this is completely non-signaling. And now what do I mean by, is it consistent? I'm going to ask whether when I take, say, g is equal to g of x1, g of x2, g of x3 equals 0, 0, 0. When I say, is this outcome consistent or will it be supported on this? I just want to give an example first before we write down the definition. What I'm going to be looking for is the following. When I restrict this thing to this context, what does that mean? I take g of x1 and g of x2. Those are the outcomes relevant for this context. I ask 0, 0. Is 0, 0 positive on this one? Yes, there's 1/2. What about the next one? 2, 3. So I look at outcomes 2, 3, 0, 0, and I ask, is the probability on 0, 0 for this one also positive? Yes. So check, check. And then 1, 3, which is again 0, 0. And I look at this context and I say, is the 0, 0 outcome positive? It is. Check. So we're going to say that this G is consistent with, or it's in the support of, this empirical model P. The empirical model, remember, is the collection of these compatible distributions. If I was to give another example, say G prime is equal to 0, 1, 0, then when I look at the 1, 2 context, I have to see if 0, 1 is supported. Is 0, 1 supported? No, it's not. So this one is not consistent with this, or it's not in the support of this empirical model. We are now in a position to write down what I mean by the support. So, have a measurement scenario. Let P be an empirical model. Then we say that the support of P is precisely all those global outcome assignments such that PC GC greater than 0 for every C in C. So, just to compare, what are we saying? We are saying, for example, in this case, we took a global outcome assignment. It's a tuple like this. We restricted to every context, and we checked that each of the corresponding outcomes, when we restrict there, here it's 0, 0, 0, so you always just restrict to the 0 outcome. You see that the probabilities are positive. That means this is in the support. Here we looked at this one, G prime. You see that 0, 0 is in the support of this one, but 0, 1 is not in the support of the first context. Therefore, this is not allowed. And so this, what you might say is that these are all global outcome assignments which restrict to possible events in the empirical model. And observe that if G is in the support, then there exists some epsilon greater than 0 such that P can be written as, so you take the deterministic distribution corresponding to that G, and you can sort of pull it out of the distribution plus some remainder. So that's kind of, there's a sort of geometric intuition there. Which is something like this. You have the space of the set of non-signaling distributions. So let this be the classical region. And then say you have some additional parts which are like this. Sorry, this should be connected. So there's a convex set. It should be convex looking. So imagine you have a distribution P, like so. You can write this P as being, you can always write any point inside of a polytope as the convex mixture of its vertices. Here, the vertices of this classical region are these dg primes. So this is the Bell polytope, but it's not the entire region. And then there's a region that's not covered by the Bell polytope. But I can write any P as a convex mixture of the vertices, the non-classical ones and the classical ones. So I have something like P is equal to some G in the support of P, B of G are some positive numbers, less than 1, but between 0 and 1 strictly. Plus some leftover piece. So when I have something that's in the support, it means that I have the possibility of writing my distribution, my empirical model P with that dg showing up there. And then the remaining piece are pieces that I can't write like that. So I can sort of interpret this as being a classical part of my empirical model. And whatever's left over is going to be non-classical. And in fact, this is going to be later what we call strongly contextual. And the strongly contextual pieces are precisely these extreme points, or they can be these extreme points, which are not classical. So the vertices that are not these classical ones, dg. So let's do an example. So in the Bell model, we have something like this. If you recall, it's good to organize this into a table like so. We have 1/2, 1/2, 3/8, 3/8, 1/8, 1/8. This is the same looking box. 3/8, 1/8, 1/8, 3/8, 1/8, 3/8. Now, we say a global outcome assignment is going to be given by a 4-tuple A0, A1, B0, B1. This is the outcome of Alice's first measurement, the outcome of Alice's second measurement, the outcome of Bob's first measurement, the outcome of Bob's second measurement. Let's put these over here. And say that we take G1 is equal to 1, 1, 1, 1. We want to check if this is in the support. So, to check this, you should look at P of x0, y0. That's this first context. These two are 0, precisely. And so what you want to do is take this global outcome assignment and on each context, restrict it to the corresponding outcome. So on the 0, 0, x0, y0, we restrict this to 1, 1, which is 1/2, equals 1/2, greater than 0. Okay, so now we repeat this for the rest of the context. We have P of x0, y1 of 1, 1 equals 3/8. P of x1, y0 of 1, 1 equals also 3/8. And P of x1, y1 of 1, 1 equals 1/8. Also greater than 0. So we have that G1 is in fact in the support. Now, I will claim that the following, G2, G3, G4 are all also in the support, where these are written as G2 equals 0, 0, 0, 0. G3 is 0. Let's see if I get this right. 0, 0, 1. G4 equals 1, 1, 1, 0. And let's check that these are in fact in the support. So, going to this one, on each context, I just restrict to 0, 0. And you see that this is, in fact, positive for each restriction. You go to the next one, 0, 0. 0, 1 is when Alice does her first, Bob does his second. So 0, 1 outcome is this one, positive. Next one is 0, 0 for when Alice does her second, but Bob does his first. It's 0, 0. And then we do 0, 1 for the last one, which is this, and that's positive. Similarly, for over here. And you also have that in each case, turns out that if you sort of compute what the minimum is, so if you say this epsilon is going to be like the minimum of these values, if you look in each case, it's going to be like the minimum of the sets 1/2, 3/8, and 1/8. So epsilon I is like the minimum of a set of numbers 1/2, 3/8, 1/8 equals 1/8 for all of them. So what does that amount to? It turns out in this case, I've actually chosen these in a particular way. There's more in the support than just this. I've just taken the ones that are useful for me, because what it means is that actually I can extract all of the classical part out using this. In general, it's not such a straightforward problem to figure out which g's to use because you can't use all of them at the same time. Because if I use, say, this one, if I use this one, say, I've zeroed out, well, you'll see what I mean by zero out, but the idea is that if you want to extract the minimum with that deterministic distribution, say I look at this one, then this is going to be 0, 0, and I'm going to have a 1/8 associated with it, 0, 0, and a 0, 1 here. This will knock this one out. So I can't choose my other g's which have a support on which restrict to this outcome because I won't be able to pull it out. You can't go negative. So you can't choose any possible g that's in the support. I chose a sort of convenient set. So what it amounts to is to say that I have P bell is equal to 1/8 sum I equals 1 to 4 of dgi. So the corresponding deterministic distributions corresponding to these, plus I'm left with something that we've seen before. So I will just write out this piece without the 1/8 associated to it, and there should be a 1/2 here because there's 4 of these. That's 1/2 and then 1/2 to make this a proper probabilistic mixture. So if I just take this piece associated with it, I have something like I have something like 1/2, 1/2, because each of them on the first context either restrict, oh, sorry, it should be 1/4 maybe. 1/4, 1/4, 0, 0. And then I believe I've set this up so that the rest of these are all 1/8. And the same, plus I have 1/2 times, and PR is something we've seen before. 1/2, 1/2, 0, 0, 1/2, 0, 0, 1/2, 1/2, 0, 0, 1/2, 0, 0, 1/2, 1/2. You can just sort of see by looking here, you have 1/4 plus 1/2 times 1/2 is a 4th. So the sum of these things is going to give me precisely this first box. And then let's see that the rest of the boxes work out. I have in all the other boxes 3/8 and 1/8, but with some flips. So if I add 1/8 everywhere here, I get a 3/8, 3/8, 1/8, 1/8. Same thing here. And then here I get the 1/8 on the diagonal versus 3/8 on the off diagonal. So this is precisely the kind of thing that this is exactly a algebraic version of this geometric picture and vice versa. And you can sort of see that when you have something in the support, it means that there is some piece of this. The coefficients are positive, but they don't sum to 1. But there is a classical piece and a non-classical piece. This is the PR box that we've encountered before. So in general, you have that for any empirical distribution, you have something like sum G in S of P, rather, B of G, dG plus 1 minus B bar, P bar, where B is equal to the sum of B of G. This is just the sum, so this is the contribution from the classical piece, and B bar is just equal to 1 minus B. I want to basically say that this decomposition is very similar to what you just have in polytope theory. If P in Rn is a convex polytope, and you have that X is in P, then you always have that X can be written as a sum Qi Vi, where Vi are the vertices of this. So that's exactly what's going on here, and I claim that this is sort of like clumping all of the non-classical vertices into one thing, which is always, it's like splitting this up. And so this remainder, P bar, must have no supports G or rather, let me just say it like this. The support of this leftover must be, which is the mathematical symbol for empty. So, and this is precisely the thing that we will define next. This is strongly contextual. So, let's see, what else can we get rid of? Let's get rid of the example, I think. So let be a measurement scenario, and P be an empirical model. Then we say that P is strongly contextual. Strongly contextual if the support of P is empty. And so there's an example that we've looked at before. This is the Popescu-Rohrlich box. And the idea is that you can show pretty easily in this case that there can't be any global assignments consistent with this box. 1/2, 1/2, 1/2, 1/2, 1/2, 1/2, 1/2, 1/2, and zeros everywhere else. So how are we going to show that this is strongly contextual? Well, in this case, things turn out to be quite algebraic. We can just say that we have some G equals A0, A1, B0, B1, and ask whether any such G is consistent with this. So, without trying to hide this too much, let's see what that looks like. So, if we have the x0, y0 context, we see that we have to have that A0, B0 is either 0, 0 or 1, 1. So this implies, so it has to be in 0, 0 or 1, 1, which implies that A0 equals B0. And then when I look at this context and this context, I also get the following. So x0, y1 is going to imply that A0 equals B1. x1, y0 is going to imply that A1 equals B0. So let's just chain together these implications. A0 equals B0. B0 equals A1. So let's see. A0 equals B0. B0 equals A1. A0 equals B0. B0 equals A1. A0 also equals to B1. So that means that A1 is equal to B1. Sorry, it took me a second. So that implies that A1 equals to B1. But at the same time, when we look at this final one, we see that the probability is not supported on 0, 0 or 1, 1. It's only supported when they are different. So it means that this is inconsistent. And so we cannot have that any global outcome assignment is consistent with this empirical model. So strongly contextual. Okay, and we have one more example. Hopefully I can fit it in. Let's get rid of this real quick. So this one is coming from the GHZ scenario. So this is going to come from quantum mechanics, and it's a very interesting example that has connections to also quantum computation. So recall that the GHZ state is 0, 0, 0 plus 1, 1, 1. And also recall that there is this Pauli X operator whose action on a computational basis state is to flip it to R plus 1 modulo 2. And the Y Pauli operator has the effect of minus I, or rather, I times negative 1 to the R plus 1 modulo 2. So what we're going to want to do is actually make the following observation, and let's recall some notation, which maybe you've seen before, which is that x, tensor x, I will sometimes write as just x, 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 and similarly for x tensor y, tensor x, or anything like that, I will just write them side by side when there's no danger of confusion. And so we have that the GHZ state satisfies GHZ state satisfies x, 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 GHZ is equal to, well, what's going to happen? I apply x to each of these basis vectors, and that flips me from 0, 0, 0 to 1, 1, 1, and 1, 1, 1 goes to 0, 0, 0. So I just get back the same state. In other words, I've stabilized this state. What you're going to notice is that also I have the following relations. If I do x, y, y acting on GHZ, well, y and x both flip the outcome, so I'm going to get 0, 0, 0 goes to 1, 1, 1, and 1, 1, 1 goes to 0, 0, 0, but now I'm going to get some additional phase pieces. When I get a y, I multiply by, I pick up an I, and I pick up a minus 1. But the minus 1s are going to cancel each other because I have 2 of them. But then I'm going to get a square of this. So this is going to be equal to minus GHZ. And a similar thing happens for any combination where I have 2 y's. So y, x, y equals y, y, x. GHZ equals minus GHZ. Now, let's see why in heck this would even matter to us. We want to consider a measurement scenario, the GHZ measurement scenario. M equals x, y, sorry. Rather, let's just write it like this. I have my measurement set. Hopefully, this will not be too confusing. Let's make it some x like this. My outcome set and my context. So this is a measurement scenario where here x is going to be Pauli x1, x2, x3. The measurements that I'm going to be able to do are the Pauli on each of the qubits, x1, x2, x3, or y1, y2, y3. My outcomes are going to be plus or minus 1 for the outcomes of Pauli measurements. And my contexts are going to be precisely x, x1, x2, x3, x1, y2, y3, and so on and so forth. The ones corresponding to this, y1, x2, y3, y1, y2, x3. So I don't want to write all of them, but I think we get the idea. And what I want to do is show you that in this context, the measurement statistics that we get when we do these quantum measurements, these are going to be on different qubits, therefore they commute. And these quantum measurements are going to yield a strongly contextual, non-signaling distribution. So to compute the probabilities, we are going to, to compute the probabilities, we recall that what we would like to do is actually compute something like this. The projector onto, so when I measure this, so let's just say this first, that I'll compute the projector onto the +1 or -1 eigenspace for, or I'll write it down for each single Pauli measurement on each qubit. So that's going to be something like P of A with outcome R is equal to 1/2 I plus R times A. R is ±1. A is a Pauli on some, rather, let me write it like AI on some particular qubit. And you can check that the square of this thing is itself. So this is a projector. Now, in a context, I have 3 possible measurements. So a complete projector for each possible tuple of outcomes is going to be like A1, B2, C3, R1, R2, R3, which is just taken by taking their products. A1, R1, pi B2, R2, pi C3, R3, like this. And I'm just going to multiply all of these through, and what do I get? I get 1/8 times I plus RA1 plus R1A1 plus R2B2 plus R3C3 plus their doubles, R1, R2, A1, B2 plus R1, R3, A1, C3 plus R2, R3, B2, C3 plus all 3 of them all together, R1, R2, R3, A1, B2, C3. So this is the projector, the full thing. If I want the probabilities, what do I have to do? To get the probability A, B, C of R1, R2, R3 outcomes, I have to take the expectation value of pi A, B, C, R1, R2, R3 with respect to the GHZ state. So it's going to be, due to the linearity of the expectation values, I'm going to have the expectation value of this, plus this, plus this, plus this, plus this, plus this, plus this. So let's go ahead and compute each of these expectation values. So let's first consider the singles. If I take GHZ, XI acting on GHZ, I claim that this is 0. Why? If I take a single X or a single Y for that matter, and I just multiply it to one of these, it's going to flip one of these to 1 and one of these to 0. When I act the bra on the other side, I only am taking the inner product with 0, 0, 0 and 1, 1, 1. Therefore, 0, 1, 0 is orthogonal to both of these, and 1, 0, 1, for example, is also orthogonal. So you get that this equals yj. By the same argument, you get that all the doubles are also 0. So terms like xi, xj equals xi, yj equals yi, yj equals 0 as well. What's not 0, though, are the triples. Why? Because we already wrote down that the triple acting on GHZ is GHZ itself. So when I take the bra of this, I'll just get 1, minus 1, and minus 1 for the rest of them as well. So I have that for the triples. I have xxx equals minus x, y, y equals, I can write it all, minus yx, y equals minus yx equals 1. Which is just to say, now what does the expression for these probabilities look like? Well, what you have is that this term, all of these terms are going to 0 except for this. So you have that the probability of xxx of R1, R2, R3 is equal to 1/8 1 plus R1, R2, R3, because xxx is precisely 1. So this thing is non-zero if and only if this product is plus 1. If the product is minus, then it goes to 0. So you only get outcomes that whose product is 1. So even though it will turn out to be the case that each of these R1 and say you measure R1 and R2, you can interpret those as being entirely random, but the third outcome is strongly correlated with the first two so that you only get the plus 1. So this one is equal to 1/4 if and only if R1, R2, R3 equal plus 1 and 0 else. Similarly, Pxyy of R1, R2, R3 equals Pyxy of R1, R2, R3 equals Pyx of R1, R2, R3, which is equal to 1/4 if R1, R2, R3 is minus 1, because in this case, you'll have that it's minus 1 here because this expectation is minus, and then 0 else. Now, the idea to show strong contextuality is going to be the following. Assume that there is some g equal to a1, a2, a3 for the x's, and b1, b2, b3 for the y's. Assume that there's some global outcome assignment. And now what we want to do is to require that the restriction of these corresponds to when the probabilities are non-zero. So in the xxx case, you have to have that the outcomes restrict to something plus 1. in the XYY, YXY, YYX case, you have to have that the product of the outcomes is odd. Sorry, this should be -1, which is very important. So, in particular, it should satisfy such and should satisfy. Well, in the XXX case, you should have that G restricted to this context equals A1, A2, A3 should be such that their product A1, A2, A3 equals +1. In the XY, Y case, you have that G restricted to XYY should be A1, B2, B3. Then we require that to be positive on this context, their product should be -1. So A1, B2, B3 equals -1. Similarly, YX, Y, G restricted to, YX, Y equals B1, A2, B3. And we require that B1, A2, B3, their product is -1. And YYX, G restricted to YYX is B1, B2, A3, and their product, in order to be supported, should be B1, B2, A3 equals -1. In particular, we have that the global outcome assignment must satisfy this triple, or this set of equations, A1, A2, A3 equals +1, A1, B2, B3 equals -1, B1, A2, B3 equals -1, B1, B2, A3 equals -1. I claim if I multiply all of these together, what I'm going to get is, if I multiply all of these together, what I see is that each thing shows up twice. So A1 squared, A2 squared, A3 squared, B1 squared, B2 squared, B3 squared. And if I multiply all these together, 1 times -1 times -1 times -1 equals -1. I have something on the left-hand side that's squares to 1. I have something on the right-hand side that's -1. Therefore, there is no consistent global here we have in quantum mechanics that you have a tripartite state which you cannot assign a consistent global value assignment to.